Thanks, Yor. So good afternoon, everyone. Today we are going to talk about the new cost-based optimizer in Spark 2.2. This massive effort behind essentially re-architecting Spark's Catalyst optimizer is a result of almost an year-long collaboration between Huawei and Databricks with tremendous input from the broader Spark community. This deep dive talk is divided into 2 sessions, and it has 4 speakers. We have Ron and Zhenhua from Huawei, and then we have Wenchen and I from Databricks. So here is an overview of this talk. In the first session, Ron and I will try to motivate the whole need of a cost-based optimizer. And then we'll try to talk about the statistics collection framework in Spark and the slew of cost-based optimizations that it enables. And then in the next session, Zhenhua and Wenchen are going to put this all together and try to demonstrate the cost-based optimizer's effectiveness by showing you results from the TPC-DS benchmarks and a live demo. Now, at a high level, let me just try to motivate this talk by explaining how Spark executes a query. So when a user writes a query, either in SQL or via the dataset or the data frames API, Spark, first of all, converts this query into a logical plan. Now, a logical plan is nothing but an internal representation of how Spark sees the query or the user's intent. Once we get this logical plan gets applied a series of transformations to kind of like structure the plan and make it more optimal. And the goal here is to come up with an optimal physical plan. This physical plan is then code generated into a DAG of RDDs that then gets prepared for execution and can reference a wide variety of data sources. Now, the focus of this talk is actually going to be in this green component, which is the optimizer. That is the component that applies a series of transformations on the logical plan to come up with the most optimal physical plan for the query. Now, here's another example to further drive down this point that I just mentioned in the previous slide. So here we have a user query. The user first tries to create a data frame called events by reading a bunch of log files. This data frame is then joined with another data frame called users, and the output is then grouped by on 2 other columns. We have location and we have status. Now, each group is then aggregated. We calculate the average duration for each group, and whatever we get, the final answer is then filtered on such that we basically prune out or remove all the rows that do not have an error in it and only keep rows where status is equal to error. Now, once we have this user query, the first step, as I mentioned, Spark tries to convert this query into a logical plan. In this case, the logical plan is just an internal representation of the user's program. So you see a bunch of scan nodes followed by a join node, an aggregate node, and a filter node. Once we get a logical plan, then Spark applies a series of transformations to convert this logical plan or the initial query plan into an optimized plan. So in this particular example, you can just see that we've pushed the filter right from the top near to the scan because we want to prune out unnecessary data early in the query. Just a very, very basic and simple optimization technique that's used in databases. Now, in Spark, the goal of the optimizer is just to minimize the end-to-end query response time. This is the goal function that we operate under. And in order to achieve this goal, there are 2 sets of guiding principles or the key ideas to establish an intuition. First, Spark tries to prune all the unnecessary data in the query as early as possible. So in the last slide, we saw like an example of filter pushdown. What this was really doing is, if it's possible, Spark tries to push the filter closer to the scan node such that you can speed up and prune the unnecessary data from the query. Another example of this could be column pruning. If the query does not really depend on certain columns of the input data, you can just prune them out. The second guiding principle for Spark's optimizer is to minimize per operator cost. And just as an example, there are different ways that you can implement joins, for instance. One way is to basically broadcast. The other way is to shuffle this entire data across like many, many nodes. And it is kind of like common knowledge in databases that if one side of the relation is small, a broadcast join is actually sometimes way more effective than shuffle joins. So again, like the optimizer in Spark tries to make this like basic decisions based on these heuristics. Another example is optimal join order. Your query might have like many, many joins, and it's sometimes useful to order the joins in one particular order than just using the default order. Now, as of Spark 2.1, we had what we refer to as a rule-based optimizer. Goal of the rule-based optimizer is to basically try to transform this query or the query plan based on some heuristic rules. Now, since these rules are heuristic, they are actually not based on true experimentation. They tend to be defensive in nature. An example of this, as we already saw, was push-down predicate that tends to push the filter down to the scan node as much as possible. Another example is column pruning, which tries to prune out all unnecessary columns. Constant folding is another example. What this rule does is, like, if you have expressions of the form 1 plus 2 plus like a column or an attribute value, instead of actually evaluating 1 plus 2 on every value or row, you just basically evaluate it once and then at compile time. So again, like very simple rules. It's all based on like these transformations that get applied to these query plans. What Spark, however, does not do is that it does not consider the cost of the operator while it's trying to apply these rules. Secondly, it also does not consider selectivity when it was trying to estimate the join size. And therefore, what really happened was that Spark sometimes created suboptimal plans to actually execute the query. For instance, the join order, like if you have many, many joins in the query, is mostly decided by its position in the SQL queries. So let's say I have a table, or I have a query of the form select something from A, B, C. By default, in most cases, Spark would try to join A and B first, because that's how the query was written, and join it with C. The other example of this is that the physical join implementation, again, like choosing broadcast, for instance, over sort merge, et cetera, is based on just heuristics. So it's easy to go wrong there. So let me actually show you how suboptimal plans can actually be created in these cases. So this is an example. It's just basically based off of TPC-DS query 11 variant. In this example, we have a query which tries to join 3 tables. We have the customer table, we have the store sales table, and the date dim table. And in this particular case, if you were to execute this query in Spark 2.1, the optimal query plan or the optimal logical plan would roughly look something of this sort. So we have the store sales and the customer table joined first, because that's how the query is written. And then you would join it with the date dim table. Now let's see how or what would happen if I were to execute this query on, let's say, 1 terabyte of data. So in this case, we used TPC-DS benchmark. The data was generated using the benchmark, and we used a scale factor of 1,000. And we see that store sales table is a very, very big table. It has around 3 billion rows. Customer table is kind of like a missized table, so it had like 12 million rows. The output of join for the store sales and the customer table was around like 2.5 billion rows, so not a very selective join. And then we join it with the date dim table, which is again like a very, very small table, and we've produced 500 million rows as an output. Now, for those of you, many of you might have already noticed that if we were just simply switching the order with which the joins happened, let's say we were to basically join the store sales table with the date dim table, perhaps the 2.5 billion rows that would produce an intermediate output could actually be significantly reduced. Right? So in fact, like, I mean, to put it more concretely, let's say we switch the order of, instead of joining store sales with the customer table, we were to join store sales with the date dim table. We found out that essentially you could, like the size of the intermediate data, instead of producing 2.5 billion rows, it just produced 500 million rows. That's around 80% reduction in data. And in effect, since you ended up reducing the size of intermediate data, you actually would speed up the query. And in this case, I mean, just a toy example, but in this case, for a 4-node cluster, we saw that the query was indeed 4% faster. So intuitively, the goal of the cost-based optimizer, or taking cost into account, is to actually just try and annotate these nodes in my query plan. So ideally, if I knew beforehand, while I was compiling or executing the query, that we have these row counts or some kind of cardinalities between each of these things, we could have taken a better decision in optimizing these query plans. And the goal of this cost-based optimizer is to just try to automatically optimize or automatically figure out things like this. So in order to achieve this, we added a cost-based optimizer in Apache Spark 2.2, and this is what this whole talk would be about. We do 3 things here. First of all, we collect, infer, and propagate table and column level statistics on source and intermediate data. So just to put it more kind of like clearly, we try to annotate the query tree with these statistics all over the place, if it's possible. Then, once we have the cost, once we have the statistics, we calculate the cost of each operator in terms of the number of output rows, the size of output, and things like this. And finally, based on all of these cost calculations, we try to pick the most optimal query execution plan in order to execute the query. So with this, I would now like to introduce Ron, who would talk about the statistics collection framework that we have in Spark 2.2 and the whole set of cost-based optimization that it enables.
Hello? Hello. In this section, I'm going to talk about statistic collection framework and the cost-based optimization. Usually, in the first step, for us to estimate cost, we need to collect statistics. We need to collect statistics for the table and also for the columns. And then we need to propagate these statistics to other operator node, okay? So here, and how do we collect statistics? We created a new command, analyze table name, and then compute statistics. And this SQL command, basically, it can collect the number of rows in addition to the table size in bytes. Okay. Before Apache Spark 2.2, we only have table size. We do not have a number of rows. As for the column statistics, we use this command, analyze table name, compute statistics, and then for columns, okay, then you specify the column name. Usually, you do not need to specify all the column names. You only need to specify those column names that used in the filter condition, in the where predicate, and or it used as a join attribute, or it is used in the group by clause. And we collect the column level statistics, for the numeric, like integer, long, and the date, and the timestamp. We collect, the number of distinct value, and the maximum value, minimum value, and the number of null values. And also for this kind of data type, the average length is the same as the maximum length. As for the string and the binary data type, we collect the number of distinct value and the number of null value. And because for the string, the length varies, so we collect both average length and the maximum length. And as you know, there are several operators. And here, in today's talk, I will just talk about how we estimate the cardinality for two most complex and interesting operator, which are the filter and the join. As you know, for a condition usually is a compound logical expression. Usually you have an AND logical operator or logical operator and the NOT logical operators. And they link multiple single logical expression. And then in each single logical expression, there's a comparison operator like equal, less than, greater than, etc. And for the data type we support in the expression, okay. For the integer, double, date, and timestamp, we support like a less than, equal, greater than. Also, there's this sign, less than, equal, and then greater. This is null safe equality. Basically, it means that null can be equal to null, okay. And for the string, and for string data type, we basically support the equality and the null safe equality, okay. So here I'm going to use one example to show you how we estimate the cardinality, for a filter operator. In this case, we have a column A, and then followed by a comparison operator, followed by little b. Little b means it's a constant b, okay? Then, like in this case, column A is less than value B. Then because the CBO can help you collect the statistics for column A, so we know column A is the minimum value and the maximum value. So it depends on where the constant value B falls. If it is less than column A's minimum value, then we know that, for this case, none of the records can meet the condition. So the filtering factor is 0%. Okay. If value B falls, between column A's minimum value and the maximum value, then here, we use proration. Here you can see that we have a formula. Without histogram, then we suppose data is evenly distributed. So the formula is B's value minus column A's minimum value, and then divided by column A's maximum value minus by column A's minimum value. If constant B is greater than column A's largest value, column A is the maximum value, then we know that all the records can meet the condition. Then the filtering factor is 100%. Okay. Also, there's another case, that is column A followed by some kind of operator and then compared with column B. Both of them belong to the same table. For example, in TPC-H benchmark, you will see some query. They try to find those delayed delivery. So the condition is commit day is less than the ship day. Okay. For that case, then it depends on whether or not column A's value and the column B's value have some overlap. If the entire column A's range is smaller than the entire B's range, then we say that the selectivity is 100%. All the records can meet the condition. On the other hand, if entire B's range is less than A's range, then the selectivity is only 0%. If there's an overlap, either some range of A is smaller than B, or B is less than A, but they have overlap, then we use an empirical value, which is 33%. And then now I'm going to talk about how we estimate the joint cardinality. We are mostly interested in the inner join. For the inner join, the way we compute the number of the join output, the number of rows for the join output, when A join B on column K1, okay, the way we compute its output size is a table A's record times the number of table B's record, and then divided by the larger value between the number of distinct value in table A's K1 column and the number of distinct value in column B's K1 column. Okay, so as for the cardinality for other type of join, like left outer join, right outer join, and the full outer join, we can do that in a similar way, except we need to also factor in that when two table join, when you estimate the outer join, sometimes if a record does not produce some output, we still need to include the count, for the record. Okay, and as for the other operators like the project, aggregate, and the limit sample, the rest are kind of straightforward, and also due to the limited time, I'm going to skip here. And after we collect statistics for table and the column, and then we also estimate the cardinality, the output size, and also number of output rows for each operator. The next thing is we need to estimate the cost, and then try to pick up the optimal plan. Okay, and here I'm going to show you, some cases. Here, this is a bill size selection. Usually, when we perform the hash join operation, we try to use the smaller size as a build size. Because in the build size, we try to build a hash table. We want to use a smaller size as a build size so that it can fit in memory. And then we use a larger, use the records in the larger relation and try to probe the hash table, okay? And here, we try to join two tables, T1 and the T2. T1 initially, it has like 5 billion records and 500 gigabytes. And then T2 has 100 million records, 20 gigabytes, okay? And then before CBO, before Apache Spark 2.2, the system will make a decision based on the original table size. Then you will say that, okay, because T2, T2 is smaller, then you will choose the right side as a build size. And with Apache Spark 2.2, then here, because we also estimate the output of the filter operator, and here the filter is very selective, and only 1 million records can meet the condition. So now the left side actually is much smaller than the right side, right before join happens. Then for this case, CBO would choose the left side as a build side. Okay. Then the next thing is that, also we try to decide if we can use a broadcast join. The benefit of the broadcast join is you do not need to shuffle the large table, okay? And you only need to broadcast this smaller side. And here, in this, if you look at the lower left diagram, we try to join T1 and the T2. T1 has 5 billion records, 500 gigabytes. T2 has 20 gigabytes. Before CBO, the system will say that both of them are larger than there's a configuration parameter that, to tell you, it must be below this broadcast threshold. Then we will broadcast. So before the CBO, the system will decide to use the shuffle hash join. But after we have CBO, for this case, because the filter is quite selective, okay? And then after filtering, then the left side is only left with 100 kilobytes. So for this case, actually, CBO will tell the system to choose broadcast join. Okay. Next thing is I'm going to briefly talk about the way we handle multi-way join. We basically implemented this dynamic programming algorithm. The best way to describe this is use recursion. For any n-way join, say for example, you have a 4-table join, you can divide, left side is only 1 table. The right side is a join result of 3 tables. Or you can divide it into, left side is a result of a 2-table join. Right side is also a result of 2-table join. I mean, by describing this, it always can be decomposed into like a 2-way join. And at each level, we try to find the optimal sub-solution. Okay. And by doing this, actually, I would say that it is a little bit, the algorithm is a little bit complex, and I do not have enough time to describe this. If you are interested, please refer to this classic paper. Okay, it was published by IBM. The title is Access Path Selection in Relational Database Management System. And then now I'm going to talk about the way we define in the join cost formula. Okay, usually in a relational database system, the way we compute the cost is there are some CPU costs and also there are some I/O costs, and then you combine them with some kind of weighting factor. In our very first CBO release, we define the cost as the weighting factor times cardinality. Actually, weighting factor times cardinality, this portion corresponds to the CPU cost. because CPU needs to look at record by record, okay? And then on the right side, it's the size times 1 minus weight, okay? And the size, basically, it corresponds to I/O cost, because when we perform I/O, we usually do that at block level. So, and this weighting factor is a tuning parameter. It can be set using this configuration parameter. Spark equals CBO, join reorder, card, and the weight. Okay, so now I'm going to have Zhenhua to talk about some results of the TPC-DS benchmark and the query analysis.
Okay, thank you. In this section, I will share with you our benchmark results for CBO and include some specific query analysis in detail. Okay, for benchmark test, we use TPC-DS benchmark, which is the industry standard benchmark for analytic queries, and we use scale factor 1000, which means the size of the data set is 1 terabyte. For tests, we use a 4-node cluster. Each node is a Huawei Fusion server with 40 cores and 384 gigabytes memory. For code base, we use Apache Spark 2.2 RC. The dataset has a total of 24 tables and 425 columns. In our statistic collection test, it takes 14 minutes to collect statistics for all tables and all columns. It's pretty fast because all the statistics we collect are computed by integrating with Spark's built-in aggregate functions. Besides, as we mentioned before, in statistic collection and cardinality estimation, we only need to collect the statistics for those columns used in filter condition, join conditions, and group by phrases. So it should be much faster if we only collect statistics for these columns. Before we look at the benchmark results, the whole benchmark results for all the TPC-DS queries, let's first look at some examples to better explain how CBO can improve plans. As the first example, let's revisit our 3-table join example at the beginning, which is extracted from query 11. Now, maybe this query looks like super huge, but we only need to focus on these 2 3-way joins. This query performs these 2 3-way joins, and union the 2 join results. Now the plan without CBO looks like this. We join store sales with customer and date dim, and we also join web sales with customer and date dim. Now the join output of store sales with customer and web sales with customer, the join results are very large, about 2.7 billion and more than 700 million. As we know, large intermediate results will cause large shuffle cost and computation cost in the follow the joins. Now with CBO, we automatically switch the order of customer and data dim. Now that means we now join store sales and web sales with data dim first, and that produces much smaller intermediate results, about 80% less than before. And this leads to 1.4 times speed up. The second example is query 72. For this query, we only care about the bunch of joins at the middle. And the plan without CBO looks like this. We just join the tables one by one by the order exactly written in the original query. And we can see from join 1 all the way up to join 5, they all produces very large intermediate results, about more than 7 million to more than 200 billion. And this makes this query proceed very slowly. Now with CBO, we can see that we not only change some small tables, we change the whole structure of this plan tree. And as a result, we produce much less intermediate results, about two or three orders of magnitude less. And this gives us more than eight times speed up. Now this slide shows an overview of the whole performance of all the queries. For each query, we show its response time in blue color without CBO, and its response time with CBO in orange color. As we can see, CBO can improve many queries, and also we can see there are also many queries has similar performance with or without CBO. The reason is that some of them are very simple queries and do not need much optimization, and some of them are already written in a good join order in the original SQL query. And we also want to mention that we have only one regression, only one small regression for query 64. And for the other queries, there's no regression. And we will revisit query 64 later. Now, in this slide, we extracted those queries. CBO can give us a major performance gain. There are a total of 16 queries that CBO brings major performance gain greater than 30%. The max speed up is 8 times, and the geomean of speed up is 2.2 times. Overall, the results of CBO, the results of this benchmark test looks very promising for our first release of CBO. But of course, it still has room to improve. Now let's look back and look into the query 64. For query 64, we only need to know that it performs these 3 table joins twice in a single query. Okay. Now with CBO turned on, the first fragment of this join is like this. First we shuffle the store sales table and shuffle the store returns table and join them, and use the join result to join another table, CSUI. CSUI is a common table expression. Now in the fragment 2, due to Spark's reuse exchange mechanism, now we can reuse the shuffle result of store sales and the shuffle result of store returns, and also we can reuse broadcast change of CSUI. Also notice that we have an outer join. So with CBO turned on, we can know that the output of CSUI is very small. It's small enough to be broadcasted. So we choose broadcast hash join here. Usually, broadcast hash join can save shuffle, and so it can save more time, right? But why in this case it's 10% slower? This is the reason. When the CBO is turned off, we don't know the output size of CSUI. Okay, so we can't broadcast it. We just perform a sort merge join for these 2 joins. And as a result, remember that Spark has a reuse exchange mechanism. Now it can reuse the join result of store sales and store returns. And this in turn happens to give more time saved for this query. And this query actually gives us a very interesting finding that broadcast hash join is not always better than sort merge join. We need to consider the plan in the whole query, not just a single node. And the key of this problem is for the savings of of the outer level product hash join and the reusing of the inner join results, which one saves more. So to solve this, we need to define a more fine-grained cost model and choose the best plan based on that model with the lowest cost. And this is also a part of our future work. Okay, I think this is the end of our first session.
Excellent. Thank you so much. Please join me in thanking the presenters.
Thank you.